side and more from the theoretical or mathematical side of the subject of graph neural networks, and more broadly learning on structured data. Is the volume all right? It seems like I got all of a sudden have this booming voice, which is slightly embarrassing to me. Anyway, okay. So this is the second boot camp is going to be about invariance and equivariance, which is I think Haggai already mentioned that it's an essential component of graph neural networks, and there's three of us who are going to present this particular part. So Hannah and Nadav and me. So we all have 30 minutes. I'm just going to talk about to take the first part, which is like this general introduction to the mathematical concepts of equivariance. Okay, so this actually comes up in different, in slightly different ways in modern deep learning. In particular, the two areas or the two manifestations of invariance and equivariance, which seem to be really critical and kind of shaping entire research directions, are equivariance to continuous groups. So whenever you're learning something kind of physical or something related to the nature of something taking place in three-dimensional space, or even space-time, slightly more an abstract way, or you inevitably face these issues of the transformation properties of your learning system with respect to translations and rotations and in general the action of the group. So there's a lot of focus on this in computer vision and graphics and all the AI for science type of applications of deep learning. The other area is learning on graphs, because again, as Haggai said, there's this natural invariance property, right? So a graph is defined by its topology. Ultimately, when you're learning on a graph or you're learning about graphs, you're interested in the topology, but it's not presented to you usually in that way. It's presented in terms of the adjacency matrix. So you need to make sure that ultimately what you're learning is actually the underlying kind of abstract topology or related to the abstract topology, rather than just the vagaries of how it manifests in the adjacency matrix. And what's particularly interesting and somewhat complicates the picture, and I think we'll see more of this even in this tutorial, is that these two types of symmetries actually interact. So things get a little bit more complicated in situations where you have both, which is kind of the classical case in things like learning force fields or learning interactions between atoms in the simulation of a physical system. But just to kind of ground your intuition, these are the two things that I would like you to kind of bear in mind. Either one of them is learning something about, say, this configuration of particles, atoms, or whatever in three-dimensional space, where naturally you want to be invariant with respect to just rotating the entire system. The other one is doing something with graphs, say learning something from the kind of the graph structure of a molecule, where you want to be invariant to permutations. Okay, so the difference between invariant and equivariance, I probably don't have to drill this into this particular audience, but it's always reassuring for somebody from a more mathematical side to see one of these kind of religious symbols called commutative diagrams. So equivariance is when you have a transformation acting on some object, say this F, which in our context is just the input to a particular layer of a neural network. And at the same time, you have other types of transformations, which is like internal transformations of these activations with respect to or under the action of a group. Okay, so in the input and the output, you both have the action of a group G. Think about translations, rotations, permutations, transformations, and so on. And equivariance is when these two things, so the group symmetries, just commute with the transformation defined by say, the layer of the neural network itself. So algebraic, let's express this way, or with commutative diagram this way. But ultimately, a lot of the time, what you really need to ensure is that as a whole, your algorithm is invariant with respect to these transformations. So one of the lessons from the equivariant machine learning, but more broadly, kind of the physics approach to, or the modern mathematics in modern physics and how it describes the world, is that even in situations where ultimately you know that your system needs to satisfy invariance internally in terms of the individual layers or the individual symbols in your equation in your physics book, actually it's equivariance that you need, because in some sense equivariance just says that, okay, you have this kind of nuisance transformation acting on your data, and I allow the transformation to mess with the internal representations of my data, but at least it happens in a controlled way. So I always know what these actions are, and that is what guarantees that at the end of the day, I can ensure that everything works out fine and you get something that is, say, invariant. Okay? So for the sake of the next few slides, I'm going to consider the simplest possible kind of model for a neural network, which is this kind of feed-forward architecture where you have just a sequence of transformations, and the classical pattern is that you have a linear transformation followed by a nonlinearity, a linear transformation followed by a nonlinearity, and so on and so on. And in order for the entire thing to be equivariant, you need to have each of these steps, each of these phases, each of these layers to be equivariant. In particular, it is usually the linear part that also captures or also involves the learnable parameters, but the nonlinearity is sometimes simpler. But we need to worry about equivariance for both these classes of transformations. So when you talk about neural networks, it's important to always bring everything back to cats. So in terms of cats, what I'm talking about is that if the input cat rotates, then all the intermediate cats can also rotate or do something strange. But at the end of the day, you just get the word cat, and that's invariant to the rotations of the inputs. Okay, but of course, modern neural networks look much more complicated. You can have transformers, you can have generative stuff, you have this kind of bedazzling array of different operations. The fundamental ideas still apply the same, right? So no matter how complicated and weird the computation graph of my neural network is, this idea that everything needs to transform in a particular way or in a pre-specified way with respect to the underlying symmetries still applies. So the whole thing of building equivariant neural networks can be reduced to the level of individual neurons. And you get a very kind of crisp constraint or prescription for what we're trying to do. So here is our little neuron, and it has inputs, and somehow each of these inputs might transform under the group. But what we really want, or what we need, is that the output must also transform in a particular way. So the question is, what can this neuron be to satisfy this criterion? And in the vast majority of the cases, basically, almost all the papers that have been written on this, all the approaches that have really been seen a lot of success in applications, these transformations are also linear. So this is the key word here, and that is what allows us to just capture the whole situation in a very kind of classical mathematical framework called representation theory. So this is what I want to talk about. So in this first part of the tutorial, I'm going to be super general, right? So I'm talking about transformation groups. The reason it's a group is just because I'm thinking of a set of transformations where you can combine one transformation with another transformation. If you have a transformation, then you can also undo the transformation. Transformations combine in this associative manner. So basically, as soon as you have any sort of transformation like this, you implicitly you're talking about the group. So this is why group theory is the right branch of mathematics to start with, and it encompasses both the discrete case, so things like the cyclic groups and the dihedral group and so on, and the symmetric group of permutations, much more interesting, complicated groups, even finite groups, and then the continuous groups, in particular Lie groups and compact Lie groups. So that is going to be more of a, before I forget, I should say that here there is something that we need to be careful about, is that much of what I'm going to say in the next 15 minutes applies beautifully to compact Lie groups. When you stray outside that safe area, then things can get a little bit more complicated, and you need to be on the lookout for what it is that still works fine and what it is that starts breaking down. Okay. So I said groups, group theory, but really what this equivariant machine learning leverages is representation theory. So a representation, here I'm saying something which is, I expect in this audience is kind of totally obvious to 70% of the audience. For the remaining 30%, it might be new, so that I just need to say it because it is the key mathematical idea that underlies the whole area. So representation is a linear map from the group to invertible transformations on some n-dimensional, let's say for now, complex valued vector space, which is a homomorphism. So by linear transformations on an n-dimensional space, the pedestrian way of thinking about this is that these are matrices, right? So rho is a matrix-valued function, and then homomorphism just means that the matrix-valued function behaves the same way as the group elements do, okay? So again, there are various different ways of thinking about this, and it's not that difficult to understand why this should come up and why this should be so important. One way of thinking about this is that this is just a way of modeling the group, right? So I said group, it's abstract, scary, whatever. But the idea of a representation is to turn the group into matrices. The matrix element behaves the same way as the group elements. The matrices kind of do the same thing for you as the group elements do, but they're concrete objects. And they're also, like, computers are much better at dealing with matrices in general than with abstract group elements. So that's one reason. The other reason is that whenever the group starts doing something, usually this appears in the context of the group acting on or operating on things that live in vector spaces, hopefully finite dimensional vector spaces. And whenever that happens, the group operations need to multiply the same way as the action of the group. This is the definition of an action. So I'm already talking about a representation. So representations are the kind of link between the kind of applied, the actual stuff that happens in the, say, the neural networks with a general mathematical picture. Yes?
Something like an injectivity condition there. Otherwise, this representation could be trivial, right?
It can be, and that's and it also so yes, there's groups have, and this is where this is heading, having a whole sequence of different representations, and the first one is always the trivial one, and it's trivial in principle, but it's actually really important for whenever you do something useful with it, because that captures like the overall average of the group. So you need to make sure that that's still in there. But it's a very good one. So you can start with the trivial one, but the others are usually not that trivial. And there's only one trivial one. Okay. So the nice thing about representation theory, the kind of remarkably powerful thing about representation theory, is that it gives this very kind of canonical way of kind of classifying in what ways you can do this, like what the representations of a specific group can be. You can almost like catalog them. And in order to do this, as whenever you do kind of taxonomy of like little insects or something, first you need to say what two representations are the same, okay? So if you have one representation and you conjugate all the matrices with the same unitary matrix, then you get something that behaves the same way, so you get another representation. But this is totally uninteresting because it's really the same representation. So these representations are usually called equivalent, and we treat them as kind of the same. So this is when you see two different insects, but they are kind of from the same species. Okay. The other thing is, which when you go more into kind of dissecting these insects, if you wish, is when you take representations and pull them apart into sub-representations. So it can also happen that you have a representation and you find that again, after conjugating by a unitary matrix, which is the same as saying that you just do a change of basis, you end up with this block diagonal structure, right? So essentially, this representation falls apart into a direct sum of these two other representations. So this, again, says that, okay, this row is maybe by itself not very interesting because it's the combination of these two smaller things. So people are interested, like people pursue, the kind of fundamental representations. So a system of representations which consists of representations that are not equivalent to each other and that cannot be broken down into smaller representations in this way. So these are called the irreducible representations, and this is where the power of representation theory starts manifesting. There's this whole sequence of theorems appearing on pages 9 to 15 of your representation theory book, which says things like the following, that if you have a finite group or a compact continuous Lie group, then in any sort of situation where you have a representation that breaks down in this triangular way, then actually you can zero out the top right-hand corner. You can have another basis transformation allows you to completely diagonalize your representation, i.e. any representation is reducible into a finite sequence of irreducible representations, moreover in an essentially unique way. So I give you a general representation, and there's only one. There's a specific way in which it's composed of these underlying irreducible representations. So this is a huge simplification, and really kind of directs your attention to the irreducible representations, right? So fortunately, we might have just invented artificial intelligence, but we didn't. But mathematics has been people have been working on mathematics for a bit longer, and actually people have worked out the irreducible representations of most of the groups that we care about. So this means that you can open up the appropriate math book and look up the irreducible representations of the group that you care about. So like three-dimensional rotations or permutations or some more weird combination of them. And that tells you that like the fundamental elements of kind of complexity that you need to deal with. And everything else, or most things, you can be able to get just by combining these irreducibles. Okay. This is a classic reductionist approach to science, I guess. All right. So again, let's continue on with these really basic things about representation theory, which kind of bootstrap equivariant learning for you. Another basic, crucial result, beautiful result, is called Shor's lemma, which says that if you have one object, like a vector, in its own space, that transforms according to an irreducible representation of the group, and you have a mapping of that object to something else, like another vector, another representation space, which also transforms according to an irreducible representation, then there are serious constraints on this mapping phi. So in particular, in this scenario, first of all, the two irreducible representations have to be the same irreducible representation. And the other thing is this mapping can essentially just be the identity or the multiple of the identity. Okay? So this is it's actually not that difficult to prove. That's why it says the slightly diminutive name of a lemma. But it's exactly what we want for equivariant neural networks, right? We're going to have layers which do decompose into irreducible representations. And we're going to have linear transformations between them. This is what the layer of the neural network does. And Shor's lemma says that actually when we do this, we have really we're really limited in how we can construct this architecture, because the irreps need to transform to the same irreps, and moreover, the map is also limited. It can also only be a multiple of the identity. Okay, so this is one of those cases of where a really basic importing a really basic theorem from mathematics has super direct implications for doing practical stuff like building equivariant neural networks. So this is in my mind, this is how these things really work. That the neural network can be complicated, the data is presented in a weird form, but at the end of the day, the group acts on it linearly. That means that it acts via representation. That means, assuming that it's a compact group or a finite group, that it can be reduced into irreducible representation. So you just do the transformation and you get these little vectors which transform according to the irreducible representations of the group. And now comes the linear layer, which is also usually called the convolutional neural network, the convolutional layer of a neural network. Well, Shor's lemma tells you that the split little neuron can only do something very simple. It can only mix the components which correspond to the same irreducible representation, and it mixes them just by multiplying each vector essentially by a different constant. And these constants are the learnable parameters of the neural network. So I'm saying something really simple here, or maybe Shor is saying something really simple. And that is that what the neural network can do, what this little fictitious neuron can do, is that it kind of stacks up all the components corresponding to the same irrep into a matrix, and the convolution layer, the action of what the layer is actually going to do is multiply these matrices from the right by a learnable weight matrix. Okay, so this is nice because in general, PyTorch and GPUs are not so great at operating with abstract group elements. On the other hand, they're pretty good at multiplying matrices. And representation theory just took this math and then brought this down to this matrix level. Okay, so we stated this in 2018, but other people have stated basically the same 100 years before that in the pure math tradition, and it's for looking at it from the representation theory point of view, this is pretty clear. Behind all this, which I'm obviously not going to have time to talk about, is this entire machinery of non-commutative harmonic analysis. So this idea of reducing things into irreducible representations is a form of harmonic analysis. It's like Fourier series and all the operations. So what I just said is kind of an analog of a convolution theorem in the ordinary Fourier analysis. So there is a lot to kind of lean on and to take advantage from math. Another way to say it is that there's a generalization of a convolution theorem, and just as in classical convolutional neural networks, there's a theorem which says that if you want translation equivariance, and then the only operation that you're allowed, only linear operation that you're allowed to have is classical convolution. In the case of a group, the only operation that you're allowed to have is convolution in this more generalized group sense. Okay, now the other part that I wanted to talk about is the nonlinear part. Do I have? Okay, all right, okay. So, and as I said a couple of minutes ago, at the kind of abstract level, when you want to build a neural network, you want linear operations and you want some kind of nonlinearities, right? Because without nonlinearities, it's not going to fly. You're just going to have a massive just linear operation. That's not enough. And for nonlinearities, the neural networks community has increasingly become kind of more and more kind of simplistic and brutal. And now most people just use the ReLU. So what is the analog? How can we do nonlinearities which are also equivariant. Well, it turns out that the nonlinearity by itself, but the ReLU by itself, is not going to cut it because it's obviously not equivariant, right? So the way to think about these architectures is these little vectors in their own, all of them in their own vector space, transforming by linear operations and so on and so on. Clearly, individual coordinate dimensions don't have any meaning, so you can't just slap on a ReLU onto the individual dimensions, because that's going to break the structure. So instead, people do different things. One of them is to, okay, three things actually. Do you have all three on the slide? Again, I don't have time to describe these and to tell you all the natural references. One of them is to go back onto the group. So to go back from Fourier space in terms of the irreducible representations, to go back to something that's actually expressed on Euclidean space or the sphere or something, and do the convolution there and come back. That's a valid approach, but it has the expense of doing fast Fourier transforms all the time, essentially. The other approach, which I here call the attention approach, is to actually reduce everything to scalars, then apply whatever nonlinearity you want to your scalars, and then multiply them back into the equivariant quantities. So this is the gating or the attention approach. I think maybe Soledad is going to talk about that later in the workshop. The third one is to try and cook up nonlinearities in Fourier space. And actually that has also become popular, at least in certain applications or certain subfields of equivariant machine learning. And that is also something that is very much kind of constrained or shaped by the underlying mathematics. So the way I like to think about it is that, okay, I want nonlinearities, I want them to be equivariant. Well, what's the simplest thing that I can do is I can do polynomials, right? So now I have vectors, so that means that I can have tensor products, okay? And the good news is that when you take two of these equivariant vectors and take the tensor product, then the tensor product also transforms according to a representation of the group. But it's not an irreducible representation. So what you need is a way to bring back these general representations into irreducible representations. So this equation is a mouthful, but what it says is what I was mentioned earlier, and that is that any representation of a Lie group, of a compact Lie group, is reducible into irreducible representations. You just need to know how to do that. The name for that is Clebsch-Gordan decomposition, and it's again something that is kind of well charted for the kind of groups that people use in practice. And then this becomes like an essential component to these equivariant neural networks. So maybe the good thing that this is like the taster of what the underlying kind of ingredients of equivariant neural networks are. We need to move into more specifics, then maybe later in the week we can come back to details of, say, the Clebsch-Gordan decomposition and how it is actually relevant to graph neural networks. So with that, let me hand it over.
Is my mouse? Oh, okay.
Let's see, go back to, yeah.
Oh. Got a black screen.
Let's go back there. Yeah,
Yes.
entire screen or whichever you
Try to start mirroring.
Thank you. Yeah.
Okay, cool.
There we go.
It's a little laggy. Okay.
Is it not going?
No, it's just taking a moment of self-care time. Sorry. I think it's somehow laggier now that it's connected to the. Alrighty, cool. Thanks so much, Rishi, for that whirlwind tour of representation theory. If you tried learning that from a textbook, it would be a lot less accessible, so I'm glad to come after that. I'm Hannah, I'm a final year PhD student at MIT, and for the second part of the tutorial, I'm gonna focus on learning on geometric graphs. And so first I'll tell you what a geometric graph is, then talk about how you can get equivariance via architectural approaches, and then sort of this alternative body of approaches that get equivariance via data transforms like augmentation. So first, what is a geometric graph? Well, it's just two words, right? What does geometric mean? That means we're going to be working in three-dimensional space. So in particular, each of our nodes in our graph is actually going to be a coordinate in 3 dimensions. And we'll usually use like this xi to indicate the 3D position of node I. And then, of course, the graph part means that we have some sort of edge structure. And these can be created via really a variety of methods. And often they are created from a raw point cloud, like just from 3D data in most applications. So this could come from bonds of a molecule. You could generate a nearest neighbor graph based on the 3D structure. You could even also do like a complete graph. This is usually something that is prescribed more so than like coming from nature, except the bonds. And so what are the key examples of geometric graphs? So in my head, there are sort of two categories. There's molecules, which includes things like materials, as well as large molecules, so proteins, and small molecules like ligands. And then you also have sort of this separate body of data coming from the graphics world. So here's like, point clouds represented 3D objects and such. And these are sort of the key applications that I'm going to have in mind for talking about how you do learning with geometric graphs. So what are the relevant symmetries, right? This tutorial is all about symmetries. So of course, if you have a molecule, right, it can rotate in 3D space. And this is the group of SO3, which Risi mentioned briefly. But we also still are calling it a graph, right? And it has nodes, and these nodes can be permuted when you actually write them down as an adjacency matrix. So in addition to having this 3D structure of the graph, it's also represented by this connectivity structure with the adjacency matrix. And as both Hagai and Risi have mentioned, you can permute the rows and columns of this adjacency matrix when you actually store it as input to a neural network, and you don't really want these to affect the result of your computation. So just to illustrate that for a moment, let's say you have your input molecule. You put it into ideally an equivariant network or some equivariant learning pipeline more broadly. And let's say you're doing some energy and force prediction, which is a pretty common application in materials, as well as biological applications. So you want to predict the energy per node, the energy of the whole molecule, and then the forces applied to each node. So if I rotate the input, what do I want to happen? Well, the energy is the same, but the forces and the whole structure, for example, should rotate along with that rotation. We also still want to permute the input, and if we permute the nodes in this input, the type of the energy obviously remains the same, but for example, the forces will permute along with the input. So if you're doing a node level prediction task, of course, permutations are still equivariant. So how do we build networks that take as input geometric graphs? So for example, again, imagine you're trying to predict the energy of an input drug molecule or its reactivity or how strongly it binds to some protein involved in a disease. So I'm actually not really going to talk so much about permutations at all. The same tool is used in essentially all of these architectures, which is message passing, as has already been described sort of in the first boot camp, right? So that you have the nodes of your graph. Now they're in 3D space, but they still have to come up with some messages and exchange information with their neighbors. The reason I'm not going to talk about really anything else is that permutations are a really big group. They're much bigger in a sense than SO3. It's like factorial dimension as opposed to a finite dimensional Lie group. SO3 is technically infinite, but actually as a dimension, it's only 3-dimensional. And so permutations are really hard, and most of this presentation is not going to be about permutations because we're going to use things from the non-geometric graph world. And in addition, one sort of note about architectures is that, I guess as was mentioned, you don't necessarily have to just pass these messages between edges. It can be like larger k-tuples, like triples of nodes in the graph. So how do we handle the rotations, right? How do we build rotation equivariance into our networks that take as input a geometric graph and output some predictions? So it's all about the content of the messages and how they are passed between nodes. And overall, I cannot really explain in this presentation all of the different architectures that people have built for doing this because there are so many of them. So this is a figure from a really great survey that I'd point anyone to who sort of wants more detail than I can convey in a 30-minute tutorial, A Hitchhiker's Guide to Geometric Graph Neural Networks for 3D Atomic Systems. But here's this sort of timeline of all of these different networks that have cropped up. By the way, Rishi's worked on Cormorant, right? That was one of the very early ones, which showcases his expertise. But there are a great many, and I'm not going to try and convey to you what the tools are for building all of these. Much like I would not try and teach you how to build, how to bake in pastry school every single dessert that exists, right? We just need certain building blocks that appear recurrently in all of them, essentially. And so now I'm going to sort of just give you the building blocks for what these different architectures do without focusing on any specific architecture. So this isn't really like a literature review. It's more based on like pedagogically, what are the tools at your disposal for working with geometric graphs. And the first one is hand-designed invariance and equivariance. So you can sort of design features that you say, OK, I know that this is an invariant feature. Let me just compute it right away. So for example, the distances between points is obviously invariant to rotation. The vector distances between points are obviously equivariant to rotation. There are also things that people like to do, especially, for example, in the proteins world. They compute things like the dihedral angles between adjacent planes. So you can think of these planes as being defined by, like, say, a set of 5 points. You have like some central red node, and then you have its neighbors on either side. These define 2 planes, and you can compute the angle between these planes. So you can sort of hand compute these features and give them as input to your neural networks. But these can also be bootstrapped to make more interesting invariant and equivariant features, right? Like ultimately, you want to learn to predict the energy, and that's going to be some really complicated function of all of these pairwise distances. And there are a couple like key strategies to bootstrap these invariants and equivariants into much more expressive architectures that almost all of these different recipes use. So the key idea number 1 is quite obvious. You can do anything to an invariant, and it remains invariant. So let's say I compute all of the edge lengths between my nodes in the graph. I can put them into any function, get out new features, and they remain invariant because the inputs were rotation invariant. And for example, you can feed them into an arbitrary neural network, and there was nothing fancy done at all here. You can also multiply an equivariant by an invariant, and it remains equivariant. So if you don't quite remember like what I mean by an equivariant, you can just think of this as like the edges between nodes in the graph. So when you rotate the molecule, all of those edges also rotate. So let's just say we compute these new features, call them F, and these are all rotation invariants. Now let's multiply them by the edge vectors. So we get out this product on the right-hand side. Well, very simply, we start with something that is unchanged under rotations. And then we have something that changes very predictably under rotations. So their product also changes very predictably under rotations. I don't think I even really need to show the proof for this exactly. So that's like sort of one actually very powerful family of nonlinearities where you say, OK, I don't really know how to do something nonlinear with these like edge vectors, but I can do something very interesting with the distances. And I'm just going to scale all of my edge vectors by something invariant. And actually, a lot of like the earlier papers on geometric graph networks basically just sort of use this tool as much as possible. And it's still used in modern architectures, too. So you might say, OK, that's nonlinearities. Well, what do we do about linearities? And sort of Risi alluded to this already, so I wasn't going to spend too much time on this. But essentially, in all of these architectures, like the linearities are the easy part. It's really the nonlinearities where, in my opinion, where the complexity arises. So if you have a bunch of equivariant vectors and they all sort of rotate in the same way, and again, these vectors are like activations in your neural network, like intermediate nodes. I shouldn't say nodes, intermediate activations in your neural network, you can basically just linearly recombine them. So it's just a matrix multiplication once again. So I'm not going to tell you anything more about the linearities, but we might be interested in more expressive nonlinearities. So for this, we need the representation theory of the rotation group, so SO3. And this is really not going to be super detailed. I just want to give you, again, a sense for like what the tools are that are at your disposal. So recall, a representation specifies a vector space and how the group acts on it. So for example, in our favorite molecule example, which is the only example I really use, your vector space is n by 3 matrices, where n is the number of points and it's 3 spatial coordinates. And the action is very standard, right? It's just like you rotate the whole molecule at once. That is a representation, and that is sort of the most common representation that we're interested in. And what you may recall from the last half hour is that tensor products are a really nice nonlinearity from an equivariance perspective. So if I take 2 representations and I take the tensor product with them, this actually becomes an object that we can reason about very, very precisely. So there are all sorts of nonlinear things that you could do to 2 representations, and we have no idea what it does. But tensor products, we do know exactly what it does and how to sort of maintain equivariance. What this sort of translates to is if you take elements of each vector space. So again, think of these V's as neural network activations. So these rows are like parts of the problem definition of how your group acts on different spaces and different objects. These V's are actually examples of objects, and this says that if you take the tensor product between them, you get something equivariant. So if I rotate V1 and I rotate V2, and then I take the tensor product, that whole tensor product also, in a sense, rotates. I think this is probably a little bit too much detail for everyone who hasn't seen this before to really be like deeply, deeply understanding. So the TLDR is that you can sort of bootstrap your way to more expressive equivariant nonlinearities. So if you start with two equivariant things, like two edge vectors, and you take tensor products between them, you can sort of get bigger, more expressive equivariant activations out of this. So this is maybe like one level above gated nonlinearities as a more expressive nonlinear operation you can do. And I think I'm actually going to skip this, but this is some detail as to, well, what do you do with this tensor product? It's by this sort of change of basis that you can decompose it and keep track of your activations in a more structured way. So right, the TLDR here is after you take all of these tensor products and you build up these giant vectors, you can break them back down into smaller vectors using this representation theoretic concept. So again, this is sort of a whirlwind tour, very high level. These are the types of ingredients people use. And for SO3 in particular, I think the only thing I really want to convey again is that these representations are well specified analytically, and we can compute them and use them. And if you try and read one of these papers, what you really need to remember is that L is like a very important variable name. Everyone calls it L. They're using them to index these irreducible representations, and the dimension is 2L plus 1. So you'll see papers that say, like, what L do we use? That means, like, how big of an activation do they store? The higher the L, the more like memory intensive these architectures are. But right, just in brief, this is sort of what the representation theory of SO3 looks like. They have an analytic known form. The biggest one used is usually called capital L in papers, and bigger L is more expressive, as Nadav will sort of mention in his part, but also more computationally intensive. And one interesting thing to note is that if you look at the middle columns of these representations, so which again, these columns are like functions over the group, but you can sort of interpret them as spherical harmonics. And this is one more critical ingredient in the equivariant, the very wide equivariant network literature. So the spherical harmonics are spherical functions, and they give you an orthogonal basis for functions over the sphere. But they actually do arise from the representation theory as well. The important thing to know about them is that they give you this analytic, very well-known set of equivariant functions. So in the sense that if you choose some point on the sphere that you're evaluating these functions at, and then you rotate that point on the sphere, we know exactly how the spherical harmonics will rotate too. And it was actually sort of shown that this is in some way like a very reasonable choice of functions that do this. And so if you were to put all of these things together, which of course I'm just giving like a really quick overview of, we're trying to build a message passing network, right? We're trying to make it work with geometric graphs. The only thing we really need to specify is like, what is the space of messages and how do they interact with each other? And so what I've sort of tried to say is that the space of messages can be indexed by these representations that are coming from the representation theory of SO3. So in very concretely, like for each node, you have like a one-dimensional vector, a three-dimensional vector, a five-dimensional vector, right, going up to some capital L. That's like literally the shape of the vector that you're often storing, although many common architectures like only go up to three, like just one-dimensional invariance and three-dimensional equivariance. And then there's a question of how these messages are interacted with each other in a way that sort of preserves symmetries. And I claim that amongst all of these very diverse architectures, essentially all of them just use some combination of these ingredients. So one is this gated nonlinearity, where you do something interesting to your invariants and then just multiply them. Sometimes they'll use a tensor product, which gets a little bit fancier in the representation theory. And then linear recombination is sort of this basic, obvious thing that comes from, that's used everywhere. And again, this is from this like Hitchhiker's Guide to Geometric GNNs paper. Essentially, right, what you do, I give you like a point cloud, you generate your graph, you maybe embed the nodes in some way. This interaction block is what I sort of tried to explain. Like sometimes it uses representation theory, sometimes it's more like gated nonlinearities and such. And then there's some output block. And again, I would direct you to this survey paper for like far more details. I think 30 minutes is not really enough time to really give you like a very, very deep understanding. But hopefully This illustrates, I guess, another figure taken from the survey papers, that in this wide world of different, very bespoke architectures that people have designed for like working with molecules and working with graphics data, you can sort of characterize them all in different ways. So here, on this x-axis is the tensor order of the features. This is that L. So I told you they always use L, and you can just choose sort of how expressive or how big do you want your activations to be. That clearly like separates out several of these different architectures. And then on the y-axis, this is more of like a message passing parameter. Like how many nodes at a time do you consider when you're computing these messages? Is it just 2? Is it more? Are you looking at angles or dihedral angles, et cetera? And so this is like roughly the space of these equivariant architectures. And if you wanted to use a specific one for your application, hopefully this gives you some confidence that you actually can understand sort of what any specific one of these is doing. So is this the only way to enforce equivariance, right? This was kind of complicated. This looks very different from the transformers and message passing that you might be familiar with. Are there sort of model agnostic strategies that you can use to get these symmetries without having to have like a PhD in representation theory to really understand them? And if you're feeling like very confused by the first half of this presentation, which is super understandable, then it's a good chance to start again. So one really obvious choice is augmentation, right? So augmentation has a long history in computer vision, and the idea is just I give you some input image, and you hand construct a set of transformations you can apply to the input image that you think fundamentally don't change the identity of this image. So as Risi said, we always have to bring it back to cats. So if you have this input image of a cat, you can apply all of these transformations, which to a human do not change the fact that this is a cat. Like making it grayscale does not turn it into a dog. And so we can do this very specifically for group equivariance too, except now we have a molecule instead of a cat, which is very sad. So you start with a molecule, and now instead of applying some sort of blurring or color shift, we just apply a random rotation to it. And now we can input it into like our arbitrary network, right? And so a pro of this is that it's very easy to implement. Like it requires no expertise, and it's compatible with any downstream architecture, including architectures that have been really well engineered and established, not just in the sort of equivariance or even the graph community. A con of this is that if you're working with rotations, then it potentially takes longer to converge because you're sampling a new rotation every time, but it doesn't just immediately capture the fact that your pipeline is supposed to be invariant to rotations. Like you have to show it many augmentations for it to figure out, oh, okay, this problem is actually like, the rotation is actually a nuisance variable. I should ignore that. That's something that has to be taught. And ultimately, you're not getting any guarantee of symmetry. You're trying to teach the network to be symmetric, but you have no guarantee that on out-of-distribution data, it actually knows to sort of respect rotation symmetries again. Yeah.
Is there any theoretical work that shows, okay, you need so many argumentations, so many samples, such that you kind of converge to?
I believe that there is some work. So there's like this paper by Doberman et al. On like the statistics of data augmentation, essentially. And I think roughly, if I'd have to check the details, but I like usually these things like in theory would scale with like the group size. However, in practice, I have some colleagues who have been looking at like very empirical studies on this sort of thing, and it seems like they might actually learn invariance like faster than would be predicted. Yeah, but I think the strong theoretical results are usually like, of course, for like fairly simple settings, like at most kernel learning, as far as I remember.
Thanks a lot.
Yeah. Any other questions? Okay, cool. I should also note, right, going back to this thing of like permutations are a much bigger and harder group in many ways than rotations, that like this augmentation strategy, as I'll say in a moment, has been deployed like quite widely for rotations. And as far as I know, effectively not done at all for permutations, right? Like this is just such a large group that like using message passing architectures or transformers has worked much better. But there are some fairly high-profile cases of augmentation, which have been like fairly divisive in the community. Perhaps the biggest one being AlphaFold 3. So if you're not in the know on this, AlphaFold 2 used like sort of these bespoke equivariant architectures, and then AlphaFold 3 came right in and did like diffusion on raw 3D coordinates with augmentation, and so everyone was kind of unsure exactly what this would mean. Another case that I heard about recently, just in my sort of biased intake of information, was these all-atom diffusion transformers, more from the material side, that also sort of did ablations with equivariant architectures and found that at scale, it was actually better to just do augmentation when you had the compute budget for it. And so overall, now this is my opinion, not clear fact, but I would say that the jury is still out between these very bespoke equivariant architectures and augmentation. So a lot of practitioners are sort of full speed ahead on augmentation, but you can look at these sort of materials benchmarks like MapBench and Open Catalyst challenges. And currently, I did check these like when I made this presentation, the top performing architectures are still equivariant, like sort of specialized things, not just like totally generic transformers. And so there's sort of this trade-off where in the history of the literature, we could build equivariance into the architecture, and this was super smart and fancy and also a little bit hard to get people to use. Or we could do, unless you like really are very into it already and embedded in the field, or we can do data augmentation during training, which is very easy to implement, but you basically get no guarantees from. And so I want to tell you really briefly about this alternative approach that I think there's a lot of, well, full disclosure, I've worked on, but I also think is, and many people have worked on, but I think is an interesting sort of interpolant between these two. And that's going to be canonicalization, and this is another way of putting equivariance into the data preprocessing. So when I say canonical, what I mean is sort of things having a preferred orientation. That's sort of the canonical version of how that thing can be oriented. So for example, if you imagine a picture of a balloon, there's sort of this canonical orientation of a balloon where like the buoyant part is at the top. You never see a picture of a balloon, or very rarely in these other orientations. And if you had a sort of procedure for imposing canonicalization on your inputs, this would give rise to equivariance in a very simple way, right? So consider back these pictures of a cat's head. I give you like a regularly oriented picture of a cat's head. You canonicalize it yourself. It stays the same. You put it into a network, doesn't matter. But now suppose I give you like some random orientation of the cat's head. You are now going to go in and undo that orientation according to your definition of what the canonical orientation is. So you've sort of taken the sideways cat and you've made it right side up. And then you put it back into a network, and of course you get the exact same output regardless of the network architecture, because you're literally giving it the same input. So you, as sort of the data processor, are going into this input and undoing any group nuisance variables, any rotations, and making sure that you give the input sort of a regularized, like standardized, so-called canonical input every time. And so of course this output is invariant. And right, this is something that's happening at the data preprocessing level. So if we were to compare this to equivariant architectures, it's compatible with any downstream architecture. It's a pre-processing step, so you can sort of still, for the heavyweight, GPU optimized part, you can use existing optimization practices, and it only affects the input and output. Now, as a sort of detail for connoisseurs, how do you actually do this canonicalization, right? Suddenly that's where all of the intelligent thinking is put into, is in this data preprocessing step. For a balloon, I sort of told you can define it in natural language. You put the round part at the top. For something like translations, right, you can sort of center it. This is like the thing that everyone does to canonicalize with respect to translations, such that if someone gave you like an uncentered molecule, you would just center it first, right? Everyone does this essentially without thinking about it. Now, how do you canonicalize with respect to rotations, right? That's sort of the aspect of symmetry and geometric graph learning that I've tried to convey has the most maybe room for innovation in it, since permutations are basically already handled by the ordinary graph learning literature. And so it might not actually be clear how you should canonicalize this. So you might say, oh, I could learn how to canonicalize it with a network, and that's true. A lot of people have done this. But let's just, as a thought experiment, go through how you would hand design a canonicalization with respect to rotations. So again, just to reiterate, the problem here is like I'm going to give you a molecule, and you need to give me like a computational recipe for how you're going to rotate that molecule such that it's always rotated into the same position. Like if I gave you a rotated version of it or a different rotated version of it, you process those all into the exact same input. So there's some heuristics you might come up with. So you could say, I'm going to take the furthest atom, and I'm going to put that on the x-axis, right? This is a perfectly reasonable thing you can do. This is canonical. One difficulty that arises here is I could slightly perturb this input molecule, and then suddenly the furthest away atom is no longer this blue atom. Now it's the gray atom. And what that means is when I canonicalize it, it's still a valid canonicalization, but these two outputs are very different, right? So this is sad. Why is this sad? This is discontinuous because we slightly changed the input, like our input data, but we got a very different preprocessed version of that input. Now, why is this bad? I will say, like empirically, it remains to be seen exactly how bad it is, but similar to adversarial examples for machine learning, this is bad because we like continuity, because we think that the ground truth function should be continuous in some way. Like you shouldn't be able to imperceptibly change an input like this panda and get a completely different output prediction. This goes against our sense of like what is correct. And you might ask, how fundamental is this problem? What if we were smarter? Unfortunately, work that I've done with Nadav and Jonathan Siegel indicates that this is actually not a solvable problem. Like in some cases, there's just no continuous canonicalization, even if you were really smart about how you chose it. But you shouldn't lose hope on this, and this is where I think there's a lot of room for innovation. It turns out there's actually a trade-off between computation time and continuity. It's not all or nothing. And so the picture here, I think I have a few more minutes, perhaps 5, okay. Canonicalization, right? Sounded really nice. It was very cheap. You do it once to your data, and then you put it into an arbitrary network. But unfortunately, it's unavoidably discontinuous. And this was something that wasn't necessarily known. People were sort of using this in their pipelines beforehand. And then on the other end of the spectrum, we have full data augmentation, which everyone loves who's not in this community. Or a lot of people are very happy to use it because it's super easy, and it's totally continuous. But it's very expensive, and you get no guarantees out of it. It's fully offloading to learning unless you actually completely sample the group. But it turns out that in between these two, there's this approach called frame averaging, which of course we did not come up with in this paper, where it sort of interpolates between this really cheap discontinuous thing, which is canonicalization, and this very expensive continuous thing, which is full data augmentation. And the picture of this, by the way, this came from a paper, at least the application in machine learning, as far as I know, came from this 2021 paper by Omri Puni et al., is basically that when I give you some input, I'm not just going to pre-process it in one way. So in a canonicalization version of this picture, this summation only has one term in it. I'm going to pre-process it in several different ways, and I'm basically going to take the average of the forward passes of the network through all of those. So here, lowercase f is your neural network, capital F is your frame, which requires a little bit more detail to explain, but it gives you some subset of rotations. And the number of terms in the sum is how many forward passes of your network you have to do. So when it was only one, it was super cheap, but that was discontinuous. When it's the whole group size, it was definitely continuous, but that was super expensive. And now when this sum is just over some subset, it's somewhere in between cheap and expensive and continuous and discontinuous. Yes?
So how do you select the subsets? There are some...
Yeah, so the restraint on this calligraphic f for this overall function to be equivariant is that it has to be an equivariant function. So when I give you an x, you give me a set of orientations for it. And when I rotate the x, all of those orientations have to rotate too. So you can, for example, people can use principal component analysis to do this often, and you get a frame of size 8. You can also try and learn the frame, but yeah. PCA is probably the most easy example to picture. I'm going to maybe just go quickly through this illustration. So what happens now with their cat, instead of canonicalizing it in one way, we canonicalize it in several ways, right, is one way of thinking about it. You get out several rotations. You have to do a forward pass for each one of them. And then you get sort of a histogram of outputs of the neural network, and you take the average of them. But still, if you now rotate the input, because of this equivariance property of the frame, as a set, the things that you're inputting to this network stay the same, and therefore this is still invariant. And we can prove this in a bit more detail. I realize this was maybe not enough detail for you to fully believe it in your heart yet. But just to give you a sense of this picture of where there's room for innovation, even more general than frames, you can also introduce randomization in how you choose these poses. And sort of by randomizing, what we show is that you can preserve continuity and it remains cheap and flexible. And sort of we show this on the theory side, but actually other papers have already been doing this and getting interesting results, I would say. These are 2 examples, so for a materials data set and sort of just generally on graph benchmarks. And it turns out that if you randomize a little bit, it seems like this might be the solution to this problem. Randomization, we can formalize as a weighted frame. In theory, there's some benefits to this, so I'm just going to skip that and just say before we go on to Nadav's section that I think there's a lot of exciting directions. Certainly, you can still focus on designing new architectures, but essentially, as Risi conveyed and hopefully I conveyed in the first half, they're all very constrained in what they can do. There's this set of building blocks, and you can put them together in different ways, and you can engineer it super well or not super well, and this can make a difference. But it's essentially established what you can do in the architectural space, and people have tried this. Something that I think the debate is still open about is if you should put it into the architecture or if you should do some sort of data processing. So for example, I think there's still a lot of open work on the augmentation side to say, how well does augmentation work in more complicated settings? You can try and construct more efficient randomized canonicalizations to prove something about. I would say this continuity problem, although it's very true theoretically, it's unclear right now like how much it matters, in the same way as like adversarial examples, it's unclear like how much they matter in practice. Same for continuity, that's like a very open direction. Something I think is super interesting is thinking about permutation canonicalization in language models, which I'd be happy to chat more about. And then I think I'll just leave it there. This last bullet point is sort of a plug for my lightning talk tomorrow, so I'll just leave that. And Nadav will now tell you about some other interesting directions on expressivity and universality. So thank you. Oh.
So I need to
Yeah, you need this.
Okay, the microphone working? Sounds okay, right? Okay, thanks. So the last part, and after I had lunch, and it's a good point again to join. Okay, so I'll be talking about new things, although they're also very related. The clicker doesn't really work. Let's see. 1 second. Okay. Wait. I'll live without the clicker. Okay, right. So I think So the first two-thirds of this talk, we're talking about different aspects of how to build these equivariant models, and in general, using this analogy from Chagai, probably from our PhD advisor, there's a zoo of equivariant models. There are many, many different equivariant models, and so you sort of have to navigate this world and decide what you're going to use, or what's fit for different applications, how you're going to choose between them. And the most sensible and common approach is that the proof is in the pudding. So if you make pudding, the proof is, whether it's good or not, is you eat it. And if you're making a learning algorithm, so you want to have something like this, where you want to show that this new algorithm you made or something like that, your new model, performs better than other models. Okay, but here we're doing theoretical stuff, right? And we're sort of going to talk about an alternative, more theoretical approach, which has the advantage of being less maybe dependent on the exact ways something is implemented or the hyperparameters chosen, which is working via theorem. So, right, in many of these equivariant learning papers, you'd have a theorem that looks like this. This and this equivariant architecture is a universal approximator of permutation invariant functions. And often the proof technique to use, this is the most popular proof technique in NeurIPS, that you write that the proof is in the supplementary material, and sometimes it really is. Sometimes it's even true, but this is very rare. And what I want to talk about is the property of universality. So of course, there's in the theory world, there are many things you can talk about, and maybe generalization will be covered later on. But I want to talk basically about expressiveness, just like Chagai was talking about before, but sort of in a different flavor. Okay, so maybe the inspiration for this is this well-known result from the 90s, late 80s, that neural networks are universal, right? So multi-layer perceptrons can approximate all continuous functions. And basically, we'd like to, now we're building equivariant neural networks for whatever equivariant task we have. And we'd like to have these new G equivariant models. We'd like them to be universal, which means they can approximate any G equivariant function. So that's a goal which often people talk about. Right, so we want to see if, if the models which we know of, or new models which we build, do they have this property? Okay, so that's essentially the goal, or what we're going to be discussing. And I'm going to talk about the same type of data types we'll be talking up till now, but I want to sort of define my own notations. Okay, so I'm going to talk basically about point clouds or graphs. A point cloud will be, a collection of n points in Rd, but usually D is 3. And you have symmetries you're interested in, which are basically either rigid motions, right? So you can rotate and translate, or permutations. Okay, so you can change the order of the points. Again, this was talked about. We talked about this before, right? And this is the formulas, right? And again, so there's sort of the distinct cases of if you're interested only in rigid motions or only in permutations or both of them together. In practice, you're interested in both of them together, but it's easier to talk about them separately. So we'll do that too. And then there's the world of graphs, right, which we think of as basically we represent them using the edges or adjacency matrix or something like that. And we want to be, if we relabel the nodes, we want to get the same result. We want to be invariant or equivariant to permutations, right? And an important distinction, which probably most people are aware of, but that here, when we're talking about graphs, we're talking about basically matrix, or it could be also a tensor, where you have two indices which correspond to the nodes, and we're permuting both of them together. When we're talking about point clouds, we're talking about endpoints, and we're just permuting. There's only one index you're permuting, and that's sort of easier in the context of what we're going to be speaking of. Okay. Okay. And if time will permit, we'll maybe also I'll say something about geometric graphs, which is essentially point clouds and graphs together, which is what Hannah was talking about. Okay. So I'd like to say that there are three paths to universality. This is, you can define this in different ways. This is for example, in this well-known paper by Yarotsky, he talked about two paths to universality. I want to say there are three, but the ideas perhaps are the same. One is group averaging, or generalized group averaging. The second is equivariant polynomials. And the third is the notion, of orbit separation. 1 second. Here we go. OK. So I'll start with generalized group averaging. OK, so this is, again, it's returning to what Hannah was talking about at the end of the talk. OK, so if you want to build a universal equivariant model, one very easy way to do this is assuming you have a canonicalization, you can take an MLP, which we said can approximate any continuous function, and you sort of plug in the canonicalization. That gives you an invariant model, and it can also approximate any invariant function based on the universality of MLPs. Okay, so that's a very simple idea, which works theoretically. Challenges here maybe are first of all, you could ask whether you have a canonicalization for whatever you're doing, and that depends. So sort of set theoretically, you always have a canonicalization, right? And you could always, for every orbit, choose a canonical element. Doesn't necessarily mean that you have a real algorithm to do it. So that's let's say if you're talking about graphs and you want to find a canonical graph in each orbit, so that's a difficult problem. So it's not sure you can even find a canonicalization. So that's one challenge with this approach. And if you can find it, so there's this issue of continuity that Hannah mentioned, which also often it may not be continuous. Then you have in the other edge, you have the notion of group averaging. So there's the same idea, right? If you want to build a universal invariant model, you can always do this by taking an MLP, which is already invariant, and averaging it. But then the challenge is that this can be expensive if the group is big. If the group is small, it's probably a good idea. But often our groups are very large or continuous, and this can be expensive to do. Although, again, you could say that data augmentation is essentially like the cheap version of this. Okay, and then maybe this idea of weighted frames can be used in the middle. Sorry, I'm jumping again. 1 second. Okay, but again, so also using weighted frame averaging, you can also get an invariant universal approximating model. And maybe your frame will be too expensive, or maybe it will not be continuous, or maybe you can do the question with whether you can find a sweet spot there is in a way data dependent and application dependent. Yeah.
How do you get the weights?
So you could try to learn it, or it's like there are constructions which depend on the application. Yeah. I don't want to answer too much now. Okay. Okay, anyway, a second path to universality is using equivariant polynomials. So this was very popular early on, and I guess maybe still. Okay, so as long as your group is nice enough, compact or something, then you can show that any equivariant function can be approximated by equivariant polynomial. Okay, and then you can often leverage results from invariant theory, which is a sort of classical mathematical field where you know often that you can characterize what the equivariant polynomials look like, and that can maybe give you ideas how to build an equivariant model which can approximate all equivariant polynomials and therefore your function. Or you can analyze existing models like this. Okay, so here's an example. Okay, so there's a very well-known model called deep sets, which I'll introduce as we go along here. Okay, which is built for point clouds mod permutations. So so basically think of, right, we have endpoints, and you want to be invariant to the operation of changing the order. And so one well-known result, or a result from invariant theory, is that any polynomial, invariant polynomial, permutation invariant polynomial can be written in this form. So you just apply the same polynomial to each point, and you take a sum, which gives you the permutation invariance, and then you apply another permutation from outside, another polynomial from outside, and that gives you any invariant polynomial will be of this form. Okay, and using this, you can basically show that if you so this is not something people use, but if you replace the polynomials with MLPs, you actually get what people call the deep sets model, which and so you can show that this model, which is, so you basically apply MLP to each point, you sum, and you apply an MLP from outside, that can approximate any permutation invariant function and point clouds. Okay, so that's, I mean, I think in a way maybe surprising because it's a very simple thing to do, but that's enough for point clouds, at least in terms of you can approximate any invariant polynomial in any invariant function in this way. Okay, and the idea, I think, of what we just saw for deep sets, you can also do using this idea of orbit separation. I'll talk about later, but I think this notion of equivariant polynomials is mostly useful to understand universality of constructions based on tensor products and linear equivariant layers, what Risi was talking about in the first part. And so the basic idea is that any polynomial can be written as a combination of tensor products and a linear transformation. And sort of as a result, you can, using neural networks, equivariant neural networks, which use tensor products as nonlinearities, equivariant tensor products, and equivariant linear layers, you can show in various settings that can approximate all functions. Okay, so for example, there's this well-known result which talks about you can use sort of high-order permutation invariant networks for graphs, and you can approximate all functions on graphs in this way, with the only caveat that possibly the tensor dimension, the number of the ultimate tensor dimension you might need is very, very high. Okay, so it's exponential. So that's serious caveat, and this type of thing also happens in other places. So you can look at you can look at point clouds, and you look at permutations and rigid motions together, which is also relatively difficult. And there also you can use high-order tensor representations. This is our paper, and you can get universality, but you need also relatively high-dimensional tensors. Risi also has a paper like that about the Lawrence group. Okay, so this is an approach that can get you to universality relatively easily. And the disadvantage is that it needs very high tensor dimensions, usually much higher than what really someone would use in practice. Okay, and that brings us to the third path, which I think is in a way most interesting also because it's a little bit related to TCS, which is what this workshop is supposed to be about. We can talk about the notion of orbit separation. Okay, so that means, say I have an invariant function E, right? And we say it separates orbits if you have that E of x will be equal to E of y if and only if the orbits are the same, right? So invariance means that if the orbit of x equals the orbit of y, then you have that equality. And the other equality is some sort of basically injectivity condition up to symmetry. Okay, so just for a simple example, right? So say you have the action of S2 on R2. So you have a vector with 2 coordinates, and you want to be invariant to permuting the coordinates, right? So if you look at this simple function, you just take these 2 elements and sum. That will be an invariant function, but it won't be separating, right? Because say if I take the vector 0, 2 and the vector 1, 1, their sum is the same, but they're not in the same orbit. You can permute 0, 2 and get 1, 1. But if you take E to be slightly more complicated, right? You just take the sum of x1 and x2 and the sum of x1 and x2 squared. Then it turns out that this thing will be both invariant and separating. Okay, so if you have 2 different vectors and E of this vector will be the same as E of that vector, that means that they are the same up to permutation. Okay, so that's orbit separation. And the basic idea is that, so Nadav and some other people have a paper about this. Right? There's a basic idea that orbit separation is equivalent basically to universality and under conditions which we won't describe. Okay, so one thing which is nice, on the one hand, if you don't have no separation, then you won't have universality. Okay, so on a high level, the argument is that if you have 2 different objects in different orbits, and say you know that there is a continuous function that separates them, so there's some continuous function that gives x the value 0 and y the value 1, then if your invariant model can't differentiate between x and y, then it won't be able to approximate this function well. Okay? Because, and on the other hand, if you have some E which is separating, then the composition of E with some MLP will be an invariant model which is also universal. Okay? So this basically means that if you know how to do orbit separation, then you have universality. Okay? And the only question is how to do orbit separation, right? And I think really here this builds us this is the thing where orbit separation and theoretical computer science meet, right? So so if orbit separation is you want to have some function, some invariant model which gives x and y the same value if and only if the orbit of x and y are the same, you often have a similar decision problem in which you could put in TCS where you want to determine if given x and y whether they come from the same orbit. Okay? So the main example is for graphs. So for graphs, this is graph isomorphism. If x and y represent graphs, so we're going to say that if the orbits are the same, that means the graphs are isomorphic, and otherwise they're not. Okay, but there are also other examples, at least one more. So that's that. Okay, and sort of clearly, orbit separation would imply a solution for a decision problem, right? So if you have something that separates orbits, you can use it to determine the graph isomorphism problem or the decision problem. The other direction maybe is not so clear, at least theoretically. So I don't know if you have an algorithm to tell whether these orbits are the same or not necessarily you can build an E from it which has the same properties a priori. But I think in a way, if you look at what happens in the graph neural network world and much of what Chagai talked about, or some of what Chagai talked about, there's a sort of analogy you can see. So let's say we know that graph isomorphism, there's no known polynomial time algorithm for graph isomorphism, and sort of similarly, there's no polynomial time separating invariant model, which we know of for GNNs. We don't know how to do that. There's this analogy, right, from 1WL to MPNN and from KWL to KGNN. So basically, this is more like, saying these things would correspond to saying we know how to separating a certain subclass of graphs, which would sort of maybe correspond to proving approximation results for graphs with a bigger quotient space or something like that. Okay, so that's that. Now, for point clouds, we talked about, we're going to talk about graphs for point clouds. So I want to talk about orbit separation for point clouds. And one sort of nice and simple example is a rigid motion. So say we have point clouds and we're only interested in equivalence up to rigid motion, then it's sort of relatively well known that if you just look at all the pairwise distances, that's separating with respect to rigid motions. Okay, so if you have two different point clouds which have the same distance matrix, basically, then they are the same up to rigid motions. Okay, and so what this means, sorry, I pressed too fast again. Has a delay. Okay, right. So what this means in terms of approximation is that if you take all pairwise distances and you apply an MLP to that, you can approximate any function which is invariant to rigid motions by something of this sort. Okay, so that's nice. What becomes more interesting and more difficult maybe is what happens if you add also permutations, right? So if I want to be, if my group symmetries are rigid motions and permutations together, then what was going to happen is that, right, if before I said that x and y will be equivalent if and only if they have the same distance matrix. So if I add this notion of, I want to think that these and these are also equivalent, right, even though they may be up to relabeling and rigid motions, then I can say that x and y will be equivalent if and only if the distance matrices of x and y are the same up to permutation. Okay? And this basically is exactly the same permutation action as you have for graphs. Okay, so, and what this leads to was a natural idea if you want to build an invariant model for point clouds. So you can take your favorite graph neural network and stick distances, the distance matrix in it, and that gives you an invariant model for point clouds, basically like Hannah talked about. Okay, and then the question, again, in terms of expressivity, you could ask, so is this graph neural network applied to pairwise distances? Is this actually separating? Okay, this is an interesting question, right? So we know for graphs, if you put inside graphs, so none of these 2WL, 3WL, 4WL, these things always have some cases where they fail. But there's some nice results that actually show that for point clouds, so if you're only interested not in graphs, but just in distance matrices of point clouds, then these things actually will be complete as long as the graph neural network is equivalent to d minus 1 WL, where d is the dimension of the points. Okay? So usually in implications d equals 3, so that means that when for the interesting case of d equals 3, all you need is a graph neural network which is 2 WL equivalent. 2 WL is like 2 FWL. Yeah.
So you assume Euclidean distances here, right?
Yeah. Uh-huh.
What happens if the points are on a manifold or something?
Don't know.
Okay.
Yeah. So we're talking about Euclidean distance, right? So this is, I think, a very nice result from this paper. And yeah, so Pablo is here, right? I mean, a lot of people here, right? And this is the result. Yeah, this is maybe a graph which illustrates this. Never mind, let's skip this. Okay, the intuition of why this works is that, or also why it's not so trivial, but also why it almost works, right, is that if you can think of, let's look at the case of d equals 2. So if you look at, say I have a point x1, which is some fixed point, and I know the center of mass, and I know the distance of x2 both from the center of mass and from x1. So that almost determines x2 uniquely. It determines it up to reflection. So there are two places where x2 could be. And okay, so if you look at, so say you have a point cloud and you fixed x1 and you looked at all the distances from the center of mass and from x1 of all these other points. So you basically can reconstruct all other points up to this reflection. Okay. So basically, like this is like sort of what you would be doing in a 1WL version of rotation invariant thing. So this would give you, again, this gives you everything up to reflection. The challenge is to actually be able to reconstruct all of, to reconstruct things completely, not up to reflection. And for that, what helps you in a way is that you'd have not only H1, but you have all the different HJs, and somehow you can do it. It's not so simple. So I really like that. And I think, how much time do I have? 0. Huh? Okay, I want to say,
That's like 10.
I'll try to finish relatively quickly. What I think is interesting in this, there's a question of how optimal this is. Okay, so in terms of in particular, if you look at, so you want to apply, if you want something which is complete, sort of separating for point clouds in R3, so we're saying a 2WL equivalent GNN is enough. Whether that is practical for applications is sort of borderline minus, I guess. I don't know, like sometimes it depends on how big the point cloud is, right? The computational complexity, let's say, is n to the third, something like that. But an interesting thing is that there are some papers, again, from the theoretical CS world, which says that actually if you want to determine equivalence of point clouds in R3, you can solve it at n log n time. So which is very, that's fine, right? That's very efficient, right? And so the question is, so there's some sort of, but I don't know of any, plausible invariant architecture which runs in this time and you can say that it's complete and it also works well. So I feel like that's an interesting question, like whether this is doable, okay? And there's sort of a similar thing in the graph neural network world, I feel like. So if before I talked about where, what happens in TCS and in graph neural networks is similar, so also sometimes it's not so similar. So okay, this is maybe only of interest theoretically, but right, there was a very high profile result talking about that you can solve graph isomorphism in quasi-polynomial time. But the GNNs, which we know are universal, have sort of exponential complexity. Both of these probably not so practical, but okay. We have a recent paper talking about that most spectral GNNs can't separate all graphs even if they have simple spectrum. So if the spectrum is, all eigenvalues are distinct, where in the theoretical CS world, it's known that this type of problem is relatively easy. Okay, so there's a pretty simple algorithm where if the eigenmultiplicity is bounded, or especially if it's 1, then you know how to solve it in low time. And I think there's a general principle here that you know how to solve graph isomorphism simply in many instances. And can you take whatever algorithm which is very efficient for whatever low eigenmultiplicity or low degree or bounded valence, and can you the same thing as low degree. Can you take that and translate it into a GNN with the same properties? Okay, so that's sort of my vague meta question. And I feel like it's one of the reasons it's vague is that these worlds are a little different. So for example, okay, so let's skip this, right? So for example, in TCS, usually, I think people feel more comfortable with numbers with finite precision, where in invariant learning, maybe you'd prefer arithmetic over the reals. There's issues of continuity which come in, let's say, in the problem I talked about with if you want to build an invariant model for rigid motions, so these things that separate things up to rigid motions with n log n time, they're not continuous, and I think that's a challenge if you want to turn it into an invariant model. There's also this issue of for in the invariant learning world, the proof is in the pudding. You want to actually say that whatever you're doing is works. Maybe in the theoretical world, that's less of an issue. So that's that. Okay, so just I think maybe a graph to summarize what I said, and then I'll dismiss the class. So I think that if you want universal models up to invariance, so these things are easily available for point clouds if you only care about permutations or rigid motions. Then if you combine these two things together, you get something which is, let's say you can do it with d minus 1 WL, but it's not sort of, there probably still is a discrepancy between what you can, which will actually be universal in theory and what actually people would use in practice. And for graphs, this becomes even more complicated. And then for geometric graphs, a priori, this will be even more complicated. And I don't know, I guess that's it. Thank you.
Any questions? So then we have a, sorry.
One question. So what do you think is the connection between orbit separation and localization? Because I think maybe canalization is just, I think it's an orbit separation function, right? Because all the things are being mapped to
Yeah, so it's a canonicalization is a kind of orbit separation.
Yeah.
Because orbit separation is like a priori you're mapping, you could map, let's say, whatever, something in this space to something in that space. And canonicalization is when you specifically map something to its orbit,
Exactly.
and it's also orbit separating.
Yeah, I'm thinking that maybe any orbit separation function can be, formalize a, composition of a canalization with some other function. Maybe you can reparameterize that because I think it's essentially based on the, canonical version of that element.
Let's talk about it offline maybe. It's interesting. Yeah.
Does the frame averaging provide orbit separation?
It's not. It gives you universality always, yes. But again, there's this issue of whether it's continuous, whether it's really defined everywhere, stuff like that. Which you have to. Okay.
All right, so now we have a 1 hour lunch break.
Yay.
Lunch is on your own.
Sure.